October 24th, 2025. It begins without preamble, without a single warning shot. Across the globe, in the silent, cold vacuum of space and in the humming subterranean command centers on Earth, the planet's defense architecture awakens. Satellites, once dormant or engaged in routine surveillance, pivot with unnerving synchronicity. Deep space sensor arrays, instruments designed to peer into the furthest reaches of our cosmic neighborhood, lock onto a new, singular target. A cascade of classified protocols, authorizations that typically require the highest levels of clearance, are activated in a silent, coordinated sequence. The official reason given to a public barely paying attention? A comet. That's the story we are told. NASA, in its calm, authoritative voice, assures us it is a harmless celestial wanderer. The headlines, eager for a simple narrative, label its passage as a routine astronomical event. But beneath this placid surface, a very different story is unfolding. Behind the locked doors of the International Asteroid Warning Network, ION, the atmosphere is anything but routine. The network has escalated to its highest state of alert, tracking an object designated 3I divided by Atlas, with a relentless, round-the-clock intensity that is typically reserved for one thing: an impending impact. Something is fundamentally wrong with this picture. The light emanating from this object doesn't behave as a comet should. It flickers and pulses with an unnatural rhythm. Its trajectory is a hyperbolic escape curve, an arc that screams of an origin far beyond our sun's gravitational embrace, a journey from a place we can only describe as nowhere. The very chemistry of its being, analyzed from afar, is alien, a composition that bears no resemblance to anything we have ever sampled or studied within our solar system. So, the question that hangs in the air, heavy and unspoken in official circles, is this: if 3I divided by Atlas is merely a comet, a simple ball of ice and rock, then why is planet Earth reacting as though it is facing an existential threat? Stay with me until the very end of this broadcast to comprehend why 3I divided by Atlas might not be a passive visitor. It could, in fact, be an observer. If this deepening enigma has set your nerves on edge, just as it has mine, I urge you not to remain a passive spectator. Show your engagement by hitting that like button and subscribe to this channel so you don't miss a single development as this incredible mystery continues to unravel. Go to the comments and tell me where you're tuning in from, what time it is in your part of the world, and answer this: do you truly believe we are being told the complete truth about what is transpiring in the void above our heads? And if you want to be a part of this growing community, a force that helps us pursue stories just like this one, please share this video. Post it on X, on Facebook, on Reddit, or share it directly in your group chats. You are the engine that allows us to keep chasing these monumental stories. For that, thank you for having our back. Part 1. The global alert nobody can explain. Let's return to the morning of October 24th, 2025. At precisely 0700 Universal Time, the International Asteroid Warning Network, or IAWN, disseminated a bulletin. To the average person scrolling through their newsfeed, it would have appeared mundane, another piece of scientific jargon easily dismissed. A routine announcement, they called it. A significant scientific opportunity, they claimed. But the bulletin's carefully curated language concealed far more than it revealed. What they omitted from that press release is the critical question: why are planetary defense protocols, procedures meticulously designed for and exclusively reserved for extinction-level threats, being quietly and systematically activated for an object that supposedly poses zero conceivable danger to any living soul on this planet? This global effort has an official designation: the 3I divided by Atlas Comet Astrometry Campaign. Its operational window is set from November 27th, 2025, running continuously through January 27th, 2026. That is 2 solid months of relentless, coordinated, round-the-clock observation. A campaign that involves a network of observatories spanning 6 continents. Now, For those of you not intimately familiar with the IAWN, let me contextualize why this is so profoundly unusual. The International Asteroid Warning Network was established for a single stark purpose: to detect, to track, and to coordinate a global response to near-Earth objects that pose a credible threat of impact. We're talking about asteroids on a direct collision course, comets with erratic and uncertain trajectories, the kind of cosmic projectiles that could obliterate cities or cast the world into a global winter. The IAWN does not, as a rule, marshal global resources for objects that are slated to pass harmlessly through deep space. Of course, they have conducted exercises in the past. There have been practice runs, readiness drills, and calibration tests. But crucially, those events were always announced as drills from the outset. This campaign, however, is being presented to the world as a purely scientific observation initiative. Yet, examine its architecture, its logistics, its very DNA, and it bears all the operational signatures of an emergency defense mobilization. Astrometry, by the way, is the science of measuring the precise position of objects in the sky. It's a painstaking process. You gather multiple observations from geographically diverse locations, you compute the object's orbit, and then you refine its trajectory with ever-increasing precision. This is standard operating procedure for tracking potentially hazardous objects. What is anything but standard is the sheer scale of the coordination we are witnessing. Major universities, government-funded observatories, even vast networks of amateur astronomers, all have been formally requested to contribute their data. Registration for participation opened weeks ago. A high-level workshop has been scheduled. This is the exact kind of global infrastructure you assemble when you need definitive answers with extreme urgency, and you require those answers to be verified by as many independent, corroborating sources as possible. This is what you do when the margin for error is zero. NASA's official statement followed the IAWN bulletin approximately 6 hours later. It was a masterclass in concise reassurance. No threat to Earth. Those 4 words became a mantra, repeated verbatim in every television interview, every press conference, and across every official social media channel. Dr. Lindley Johnson, NASA's planetary defense officer, went on the record to state that the object's closest approach would be approximately 1.8 astronomical units from Earth. To put that into perspective for you, 1 astronomical unit is the distance from the Earth to the Sunday, so we're talking about a flyby distance of about 168 million kilometers. The Moon, our closest celestial neighbor, is a mere 384,000 kilometers away. So yes, by any cosmic yardstick, 3I divided by Atlas isn't just outside our neighborhood, it's barely on the same continent. And yet, defense satellites have been retasked. According to multiple sources within the aerospace and defense communities, individuals who spoke to various outlets under strict conditions of anonymity, classified observation platforms operated by the United States Space Force and its international partner agencies have fundamentally altered their coverage windows. We're talking about deep space infrared sensors, high-gain radar arrays, assets that are normally dedicated to monitoring geostationary orbits or tracking the satellites of foreign adversaries. These billion-dollar systems are now all pointed at a comet that, officially, poses no risk whatsoever. One source characterized the move as a precautionary reorientation. Another called it standard protocol compliance. A third, speaking more bluntly, said the current atmosphere reminded them of the frantic scramble in the 19 hours preceding the 2008 TC-3 impact, when global agencies raced against the clock to confirm an asteroid was going to strike the Sudanese desert. The crucial difference, of course, is that this time there is no predicted impact, no countdown to catastrophe, no discernible threat. So, the question remains, what exactly are they preparing for? Let's briefly discuss neo-emergency procedures, because understanding the playbook helps illuminate why the current situation feels so dissonant. When a potentially hazardous asteroid is discovered, agencies follow a strict, escalating protocol. Step 1. Verify the orbit with multiple, independent observations. Step 2. Calculate the impact probability and potential impact location. Step 3. Issue confidential warnings to the relevant government authorities. Step 4. Activate a wider network of observational resources to refine all predictions. Step 5. If the threat is confirmed, begin discussions on mitigation options, from civil defense to kinetic impactors. That is the ladder of escalation. You do not skip steps. You do not activate downstream protocols unless the upstream conditions have been met. But with 3I divided by Atlas, that's precisely what appears to be happening. The object is not on a collision course. It possesses a hyperbolic orbit, a clear indicator that it originated from interstellar space and is destined to return there. It is not gravitationally bound to our Sunday, it is a tourist, not a resident. And yet, we are witnessing a step 4 level of global coordination. We are seeing the kind of intensive data sharing and resource allocation that typically only occurs when there's a non-zero chance of an impact. Consider Apophis, the asteroid that caused widespread concern back in 2004. It garnered this level of intense scrutiny because, for a time, it had a 1 in 45,000 chance of striking Earth in 2029. That threat was eventually nullified through further observation, but the campaign that followed set the global standard for how we respond to uncertain threats. Apophis was tracked relentlessly. It was imaged with radar. Observatories around the world pooled their data, and gradually, over months of painstaking work, the cone of uncertainty narrowed until the danger completely dissolved. The 3I divided by Atlas campaign is being executed with that same intensity, that same palpable urgency, except this time, there is no uncertainty about an impact. The trajectory is clear. The distance is safe. So, what other uncertainty are they trying to narrow down? This is where the unofficial narrative begins to sharply diverge from the official one. Media outlets, particularly those with well-placed sources inside the defense and aerospace sectors, have reported on whispers of something being called anomaly detection readiness. This isn't a formal, documented term. You won't find it in any public NASA handbook. But it's a phrase that personnel working adjacent to planetary defense systems have begun to use in hushed private conversations. The core idea, as best as anyone can piece it together, is that modern defense postures are no longer solely about preventing kinetic impacts. They have evolved to include the detection of objects that simply do not conform to our understanding of the universe. Objects that behave unexpectedly, that emit signals that shouldn't exist. It signifies a paradigm shift from kinetic defense to informational defense. It's less about stopping rocks and more about fundamentally understanding what we are looking at before it's too late to formulate a response. If that sounds paranoid, consider this context. We have now detected 3 confirmed interstellar objects in less than a decade. 3. Before 2017, we had never confirmed a single one. Now, we are averaging nearly 1 every 3 years. Each of these visitors has been profoundly strange in its own unique way. Each has posed questions for which we had no pre-existing frameworks to provide answers. And with each encounter, the chasm between public reassurance and private, internal concern seems to widen just a little bit more. Perhaps our global agencies have learned a critical lesson from these earlier encounters. Perhaps they have concluded that no threat, and fully understood, are not synonymous. Perhaps, just perhaps, they are preparing for the possibility that this object, like its predecessors, is far more than it appears to be. So, we are left staring at a paradox. An object that cannot physically harm us is being watched as if it might. A campaign that is framed as a scientific endeavor is structured like a military defense operation. Official statements declare that everything is fine, while official actions suggest we are bracing for something we are not being told about. And at the very heart of this swirling vortex of contradictions, hurtling through the darkness at 61 kilometers per second, is a comet that should not be receiving this level of attention. Unless, of course, it isn't just a comet. Part 2. The object that shouldn't exist. Let's begin with the established facts. Because in a narrative as bewildering as this one, concrete data is the only anchor we have. The object designated 3I divided by Atlas was first detected on July 1st, 2025. The discovery was made by the Asteroid Terrestrial Impact Last Alert System, a network of 4 telescopes operated by the Atlas survey. The specific discovery site was in Chile, a component of a sophisticated, coordinated sky scanning program designed to identify anything unusual transiting our solar system. And 3I divided by Atlas was, from the very first observation, profoundly unusual. Within a matter of days following its detection, preliminary orbital calculations confirmed what astronomers had immediately suspected. This object was not from our solar system. Its trajectory was unequivocally hyperbolic, meaning it had journeyed from the vast emptiness of interstellar space, was now passing through our system, and was destined to eventually depart, never to return. This made it only the 3rd confirmed interstellar visitor in all of human history. That fact alone would make it a subject of intense scientific interest. But being interesting does not trigger planetary defense protocols. The orbit itself tells a peculiar story. 3I divided by Atlas is traveling at a blistering velocity of approximately 61 kilometers per second relative to the Sunday. This is extraordinarily fast, even for interstellar objects. For context, Voyager 1, the most distant human-made object, is moving at a comparatively sluggish 17 kilometers per second. This object covers the distance from the Earth to the Moon in roughly 90 minutes. Its perihelion, or closest approach to the Sun, took place near the end of October at a distance of about 1.4 astronomical units, placing it just beyond the orbit of Mars. As we've discussed, its nearest pass to Earth was at a comfortable 1.8 astronomical units. There was never any risk of collision. NASA was being entirely truthful about that. But here is the first statistical oddity. That specific trajectory brings the object to within about 5 degrees of the ecliptic plane. The ecliptic is the flat, disk-like plane where the vast majority of planets in our solar system orbit the Sunday. Think of it as our solar system's main celestial highway. Objects arriving from random vectors in the galaxy should not show a preference for aligning with this plane. The probability of such an alignment isn't 0, but it is low enough to be statistically significant, low enough to raise an eyebrow. It's akin to throwing a dart at a spinning globe from across a room and hitting the equator. It's possible, but it's also suspicious. Now, let's address the object's size, because even this fundamental characteristic is shrouded in an uncertainty that feels incongruous with our current technological capabilities. Based on its brightness and making certain assumptions about the reflectivity of its surface, what astronomers call albedo, the nucleus, the solid core of ice and rock at its heart, is estimated to be somewhere between 0.44 kilometers and 5.6 kilometers in diameter. This is an immense range of uncertainty. We're talking about an object that could be the size of a small mountain or as large as a significant city, and we cannot seem to narrow this estimate down any further because the nucleus is enveloped in a thick coma, a vast cloud of gas and dust that renders direct observation of the solid body nearly impossible. Comets are notoriously difficult to measure for this reason. You're attempting to see a dark, irregularly shaped object wrapped in a glowing, opaque fog, all while it is millions of kilometers away and moving at incredible speed. But even with these challenges, this degree of uncertainty feels like a problem that should have been solved by now. We possess powerful space telescopes. We have advanced adaptive optics on our ground-based observatories. Why do the error bars on its size remain so stubbornly wide? The coma itself is where the situation transitions from merely unusual to genuinely weird. Most comets are essentially dirty snowballs, agglomerations of water, ice mixed with rock, and various frozen gases. As they draw near the sun, the ice is heated and sublimates, transforming directly from a solid to a gas. This process creates the characteristic glowing coma and the tail that always streams away from the sun, pushed by solar radiation. It's a process we understand intimately. We have studied dozens of comets up close. We have even successfully landed a probe on one. But 3I divided by Atlas does not behave like any of those comets. First, it began outgassing far too early in its journey. He is not definitively claiming that 3I divided by Atlas is a spacecraft. He is arguing that we must keep that possibility on the table, that we must conduct the specific observations that could either rule it out or lend it support, and that we must not reflexively dismiss the idea simply because it makes us uncomfortable. Whether you agree with his conclusions or not, his central point about intellectual honesty is difficult to dismiss. This implies that some other, unknown mechanism is driving this intense activity, and we have no idea what it could be. Then there is the matter of its composition. In late September, the James Webb Space Telescope directed its powerful infrared gaze towards 3I divided by Atlas and captured data that no one was prepared for. Spectroscopic analysis, the technique of breaking down light into its constituent wavelengths to identify chemical fingerprints, revealed an extraordinarily high ratio of carbon dioxide, CO2, to water, H2O. Specifically, the data indicated a CO2 to H2O mixing ratio of approximately 8:1. While not completely unheard of in comets, such a ratio is exceptionally rare. The vast majority of comets are water-dominated. Jupiter family comets, which are regular visitors to the inner solar system, have ratios closer to 1:1. Long-period comets from the Oort cloud, those distant travelers that take thousands of years to orbit the Sun, are slightly richer in carbon dioxide, but nothing approaching this. A ratio of 8:1 suggests that this object was formed in an environment that was extremely carbon-rich and water-poor, perhaps in the frigid outer regions of a protoplanetary disk around a completely different type of star. Or, and this is the uncomfortable alternative, it suggests that the object's composition has been artificially altered by processes we do not currently understand. Polarimetry, the study of polarized light, added yet another layer of strangeness. When light reflects off particles, it becomes polarized, meaning the light waves begin to oscillate in specific, aligned directions. By meticulously measuring this polarization, scientists can infer key properties of the scattering particles, such as their size, their shape, and their composition. Observations conducted by the Very Large Telescope and other leading facilities detected what researchers described in their preliminary notes as extreme negative polarization in the light, reflecting from 3I divided by Atlas. The term extreme is not one that appears lightly in scientific literature. It signifies that the measurements fell far outside the expected ranges for typical cometary dust. It suggests that the particles suspended in the coma possess highly unusual optical properties, perhaps due to irregular shapes or compositions that do not align with the silicate dust or organic grains we have observed in every other comet. Some theoretical models propose that the dust could be rich in metallic compounds or highly complex carbon molecules. But these are just guesses, attempts to force-fit baffling observations into scientific frameworks that were never designed to accommodate such an anomaly. And then, there's the nickel. The confounding nickel. In mid-October, the Keck Observatory in Hawaii utilized an instrument called the Keck Cosmic Web Imager to obtain high-resolution spectra of the coma. They discovered narrow, distinct emission lines corresponding to neutral nickel atoms. This finding is profoundly bizarre. Metals like iron and nickel certainly exist in comets, but they are typically locked up within dust grains and other refractory materials. They do not usually outgas as free atoms. You need extremely high temperatures or highly unusual chemical reactions to liberate them into a gaseous state. What made this discovery even stranger was the conspicuous absence of corresponding iron emission lines. Nickel and iron almost always occur together in cosmic materials. They are forged together in the cores of dying stars and are distributed together throughout the interstellar medium. To find nickel without iron is like finding smoke without a fire. It strongly suggests a process of fractionation, where one element is separated from another. And that requires a very specific and controlled set of conditions. Some researchers have tentatively proposed the presence of nickel tetracarbonyl, a highly volatile compound that can form when nickel reacts with carbon monoxide under specific pressures and temperatures. On Earth, it is a toxic industrial chemical used in metal refining processes. To find it occurring naturally in a comet would be entirely unprecedented. Because natural cosmic environments do not typically create the precise conditions required for its formation. This is standard operating procedure for tracking potentially hazardous objects. What is anything but standard is the sheer scale of the coordination we are witnessing. Major universities, government-funded observatories, even vast networks of amateur astronomers all have been formally requested to contribute their data. Registration for participation opened weeks ago. A high-level workshop has been scheduled. It's also possible that millions of years of space weathering the relentless bombardment by cosmic rays could alter an object's surface chemistry in ways we are only just beginning to model. The scientific process is functioning as it should. Papers are being drafted, data is being rigorously analyzed. But the unassailable fact remains: we have never encountered a comet quite like this one. And when you aggregate all of the anomalies, the peculiar trajectory, the bizarre composition, the inexplicable emissions, the timing of it all, it begins to feel less like a cluster of random coincidences and more like a coherent pattern that we are not yet equipped to recognize. Dr. Avi Loeb, the Harvard astronomer who garnered both fame and notoriety for suggesting that our first interstellar visitor, Oumuamua, might be an artifact of extraterrestrial technology, has been characteristically vocal about 3I divided by Atlas. He has argued in numerous interviews and op-eds that the scientific community has a fundamental responsibility to consider non-natural explanations when all the natural ones require increasingly contrived and convoluted assumptions, unless, of course, the environment inside 3I divided by Atlas is not entirely natural. Let me be perfectly clear. There are hypotheses being explored that do not involve anything artificial. It is theorized that carbonyl chemistry could potentially occur in a carbon-rich, carbon monoxide-dominated coma under the influence of solar heating. It's possible that primordial materials from a different stellar nursery might contain trace metallic compounds we have never encountered before. If we only search for what we expect to find, we are guaranteed to miss what is actually there. So, this is our current situation. We have an interstellar object, only the third ever detected, that is exhibiting multiple, profound anomalies that are pushing the very boundaries of cometary science. It has an orbit that seems statistically improbable, a composition that appears alien, and emissions that feel far too specific. And in response, a global observation campaign has been mobilized, deploying resources on a scale normally reserved for credible threats to our planet. If 3I divided by Atlas is just a comet, it is, without question, the strangest comet humanity has ever witnessed. And if it's not just a comet, well, that is a sentence that nobody in an official capacity is willing to complete. Not yet, anyway. But the clock is ticking. Perihelion has passed. The object is now moving away from the sun, cooling down, and becoming progressively harder to observe. If there are definitive answers to be found, they need to be found within the next few weeks. After that, 3I divided by Atlas will fade back into the darkness from which it came, and we will be left to wonder, perhaps for generations, what it was that we missed. Part 3. The covert mobilization of planetary defense assets. Let us now return to the campaign itself, because a meticulous examination of what the IAWN is actually demanding from the global astronomical community reveals the true, unprecedented urgency of this situation. The 3I divided by Atlas Comet astrometry campaign was not initiated with the slow, deliberate pace of typical scientific research. It was launched with a call for participation in mid-October, less than 2 weeks before the object's perihelion. The stated goals, as articulated in the public announcement, appeared straightforward and almost mundane: improve positional measurements, refine orbital parameters, and coordinate multi-wavelength observations across diverse geographic locations. Astrometry campaigns are not, in themselves, unusual. They are the bedrock of how we maintain our catalogues of known asteroids, track the ever-growing population of artificial satellites, and verify the fundamental laws of celestial mechanics. What makes this particular campaign an outlier is the combination of its immense scope and its breakneck speed. The IAWN is not merely asking for data, it is demanding continuous, uninterrupted coverage. This means that at any given moment, 24 hours a day, a professional-grade telescope somewhere on this planet, is expected to be pointed directly at 3i divided by Atlas. To achieve this requires a level of logistical choreography that is nothing short of staggering, a perfect synchronization across dozens of time zones, unpredictable weather patterns, and competing institutional priorities. This is a level of operational effort that screams of something far more critical than casual scientific curiosity. The campaign's architecture includes a workshop, scheduled for late November, but the location is being kept under wraps undisclosed. Think about that. Scientific workshops are meant to be collaborative, open events. The secrecy surrounding this one is a glaring anomaly. Prospective participants must register and be vetted in advance. The data submission protocols are far more rigid and formalized than is typical, with an intense emphasis on calibration standards, meticulous error reporting, and the rapid, near real-time sharing of all findings through secured, centralized databases. This is not the relaxed, collegial atmosphere of academic research. This is the rigid, disciplined structure of institutional-grade, mission-critical coordination. It is the exact process you implement when the data is not just interesting, but vital, when high-stakes decisions may hinge on the quality of your observations, when you absolutely cannot afford gaps in your surveillance or inconsistencies in your analysis. The IAWN has, as we've noted, conducted exercises before. Back in 2018, it coordinated a global observation of the asteroid 2012 TC4 as a preparedness drill. It is this fundamental discrepancy, the dissonance between official framing and operational reality, that is setting so many nerves on edge within the communities that watch the watchers. Then we have the media coverage, which has been, to put it mildly, inconsistent with the calm, official tone. In mid-October, the New York Post published a startling article with a headline that deployed the explosive phrase, "Interplanetary Defense System Deployed." The article cited multiple unnamed sources from within NASA's Planetary Defense Coordination Office, and strongly suggested that protocols normally reserved for confirmed potential impactors were being quietly activated. Now, let's be clear. The New York Post is not the scientific journal Nature. It is not a peer-reviewed academic publication, but it absolutely has sources, and in this instance, the details provided were specific enough to suggest that someone with deep inside knowledge was deliberately leaking information. The article explicitly mentioned NEOWISE, the repurposed infrared space telescope that constantly surveys the heavens for asteroids, being specifically tasked with additional, targeted observations of 3i divided by Atlas. It referenced highly sensitive data-sharing agreements between NASA and the Department of Defense, agreements that permit certain military telescopic assets to be reprioritized under justifications of national security. It even floated a specific protocol designation, IPD-9, which allegedly governs the official response to anomalous deep space objects. Now, I cannot independently confirm the existence of IPD-9. No public documents make any reference to it. But the very fact that multiple, independent sources are now using this same terminology suggests one of two things. Either a highly coordinated leak is underway, or this is a shared misunderstanding of a very real, classified protocol. Let's discuss the specific assets that are being maneuvered, because this is where the official silence becomes deafening. NEOWISE, as mentioned, is a spacecraft. It resides in a low Earth orbit, perpetually scanning the sky in infrared wavelengths to detect asteroids and comets by their heat signatures. Retasking it to focus intently on a single object is certainly possible, but doing so comes at a significant opportunity cost. It requires burning through precious mission time that could otherwise be used for its primary mission, surveying the sky for new, undiscovered threats. Someone, somewhere, had to make a calculated decision that focusing on 3i divided by Atlas was more valuable than that primary mission. That is not a decision that is made lightly. Then there is the Deep Space Network, or DSN. This is NASA's global array of massive radio dishes, the essential communication link to our most distant spacecraft. Radar is an incredibly powerful tool for determining an object's rotation rate, its surface roughness, and for making extraordinarily precise distance measurements. but it is also incredibly resource intensive. You simply do not use the DSN for radar astronomy unless the data you seek is considered absolutely critical. Now we venture into the shadowy realm of classified assets. And here, I must tread carefully, because speculation can quickly curdle into baseless conspiracy. But let us acknowledge what we know for a fact exists. The United States Space Force operates a constellation of reconnaissance satellites with capabilities that are the stuff of legend. Advanced infrared detection, ultra-high resolution imaging, and sophisticated signals intelligence. These are the unblinking eyes of national security, designed to monitor foreign satellites, ballistic missile launches, and other strategic targets. Their full capabilities are among the most closely guarded secrets in the world, but it is entirely reasonable to assume they can also observe objects in deep space if they are tasked to do so. Similarly, a network of ground-based radar installations, some with dual civilian and military functions, can track objects millions of kilometers away. If our defense agencies decided that 3I divided by Atlas warranted their attention, they possess the tools to watch it with an intensity that would dwarf any civilian effort, all without a single word of public disclosure. The question is not whether they can watch it, but why they would. What specific threshold was crossed that justified the mobilization of these crown jewels of the nation's strategic infrastructure? One possibility, whispered in secured forums and hinted at in follow-up articles, is that our agencies are testing the real-world integration between civilian science networks and classified defense systems. In this scenario, the operation isn't about 3I divided by Atlas itself, but about using it as a high-fidelity, live-fire exercise to see how well information can flow during an ambiguous, high-stakes event. Think of it as a fire drill, except the fire is real. It's just very, very far away. The goal was to simulate how the international network would respond to a newly discovered near-Earth object with an uncertain trajectory. But that event was explicitly and transparently announced as a drill from the very beginning. Everyone involved knew the stakes were hypothetical. The 3I divided by Atlas campaign, however, is being presented as a scientific opportunity, not a drill, even though its operational structure is a near-perfect mirror image. And you cannot answer them with computer simulations alone. You need a real object, generating real data, requiring real coordination, all under the pressure of real time. From that strategic perspective, 3I divided by Atlas is the perfect test case. It is anomalous enough to be genuinely interesting, distant enough to be perfectly safe, and its interstellar origin provides ample justification for invoking exceptional measures. But this leads us to the most uncomfortable part of this hypothesis. If this is a drill, no one in a position of authority is admitting it. If this is a test of our global readiness, it is a test that is being conducted without any public acknowledgement. This means the public is being left to fill in the blanks, to guess at the motivations behind these actions. And when people are forced to guess, they do not always guess generously. This absence of transparency is a breeding ground for suspicion. It creates a fertile space for theories that might be incorrect, but are impossible to definitively disprove. Is 3I divided by Atlas being treated as a matter of national security because it is exhibiting anomalies consistent with potential technosignatures? Is there data, perhaps from those classified sensors, that suggests a level of activity we are not being told about? Or is the mobilization itself, the entire story, a stark signal that the discipline of planetary defense has now matured to a point where it operates in a parallel, classified track? Their full capabilities are among the most closely guarded secrets in the world, but it is entirely reasonable to assume they can also observe objects in deep space if they are tasked to do so. Similarly, a network of ground-based radar installations, some with dual civilian and military functions, can track objects millions of kilometers away. Not whether our telescopes can successfully track a comet, but whether our institutions can be honest with us about what they are truly seeing, and why they are looking so intently at something that is supposed to be completely harmless. Time on the DSN is one of the most precious commodities in all of science. It is a zero-sum game, scheduled meticulously months, sometimes years, in advance among multi-billion-dollar missions. Yet, reliable reports indicate that specific, high-priority observation windows were abruptly cleared to allow for radar tracking of 3I divided by Atlas. With 3I divided by Atlas, we are watching it happen in real time, and the fact that no one will officially confirm or deny the defense component of this campaign makes it feel less like prudent caution and more like something is being actively concealed. So, what are we left to conclude from all of this? The IAWN tells us they are simply improving astrometry. NASA assures us there is no threat. Anonymous media sources insist that our most advanced defense systems are fully engaged. The data will, eventually, be published. The workshop will, presumably, produce its findings. But by then, 3I divided by Atlas will be gone, a faint ghost receding into the void, and the questions we should have been asking all along will be that much harder to answer. So maybe that is the real test here. But here, in the final days of October 2025, we do not have the benefit of that hindsight. We have anomalies, we have protocols, and we have official silence. And somewhere within that silence, decisions are being made that we, the public, are not privy to. Decisions about what to look for, what to prioritize, and perhaps what to prepare for if those confounding anomalies do not resolve into something comfortable and familiar. The campaign runs through January. Insiders suggest this is simultaneously a scientific campaign and a critical readiness test. And the object at the heart of it all continues to defy every easy categorization, spewing gases we don't expect, emitting metals we don't understand, and following a path that feels just a little too deliberate to be purely random. Perhaps the mobilization is entirely justified. Operation Sentinel, a series of classified defense exercises conducted in the late 2010 seconds, reportedly included scenarios involving ambiguous orbital objects and the protocols for escalating a response. The existence of those exercises was only acknowledged long after they had concluded, and even then, the details remain sparse. So, a precedent exists for planetary defense activities that blur the line between open science and operational security. The crucial difference here is the timing. It is this fundamental discrepancy, the dissonance between official framing and operational reality, that is setting so many nerves on edge within the communities that watch the watchers. Then we have the media coverage, which has been, to put it mildly, inconsistent with the calm, official tone. In mid-October, the New York Post published a startling article with a headline that deployed the explosive phrase, "Interplanetary Defense System Deployed." The goal was to simulate how the international network would respond to a newly discovered near-Earth object with an uncertain trajectory. But that event was explicitly and transparently announced as a drill from the very beginning. Everyone involved knew the stakes were hypothetical. The 3I divided by Atlas campaign, however, is being presented as a scientific opportunity, not a drill, even though its operational structure is a near-perfect mirror image. Part 4. The official line versus the classified reality. There is a subtle art to official government statements, a meticulous calibration of language precision-engineered to inform without ever causing alarm, to acknowledge a situation without ever truly admitting its gravity. The public communications issued by NASA regarding 3I divided by Atlas are a textbook example of this craft. Every press release, every soundbite from an agency official, every single tweet sent from an official account has been honed to echo the same core, tranquilizing message, no threat to Earth. And on a purely technical level, they are correct. The object will not physically impact our planet. Its trajectory is understood with a high degree of mathematical certainty. The probability of a collision is, for all practical purposes, 0. But listen closely to the words they chose, and more importantly, to the words they are conspicuously not choosing. Notice the careful, deliberate specificity. The assurance is narrow. It tells you what won't happen, not what might. There is no mention of any potential threat to our orbital infrastructure, the fragile web of satellites upon which our modern world depends. There is no mention of non-kinetic effects, electromagnetic interference, unexpected radiation, or any of a dozen other variables that don't involve a direct impact. The statement is a masterpiece of semantic precision, designed to answer one question so that you forget to ask all the others. The European Space Agency's, ESA, public statements have been similarly, almost suspiciously, careful. They have consistently emphasized the immense scientific value of studying an interstellar visitor, the profound rarity of the opportunity, and the vital importance of international cooperation. All of this is true. All of it is uncontroversial. But behind the scenes, actions tell a different story. ESA's Mars Express orbiter, which had a meticulously planned observation schedule to study Martian surface features in late October, had that schedule quietly adjusted. The adjustment was to include multiple imaging attempts of 3I divided by Atlas, as it made its closest approach to Mars's orbital space. This significant retasking of a multi-million-dollar interplanetary asset wasn't announced in a celebratory press release. It was noted quietly in a mission log update, long after the fact. Why the discretion? If this is purely a scientific opportunity of a lifetime, why not trumpet it from the rooftops? Why not celebrate the incredible flexibility and responsiveness of our interplanetary missions? The silence suggests that someone, at a very high level, decided that less public attention on this matter was preferable to more. The Minor Planet Center, MPC, the global clearinghouse responsible for cataloging and tracking small bodies in the solar system, has been updating the orbital elements for 3I divided by Atlas with dutiful regularity. Their data is public, accessible to anyone with an internet connection and the knowledge to interpret it. But here is what's deeply interesting to those who possess that knowledge. The error bars on certain key parameters, particularly the terms related to non-gravitational acceleration, have been fluctuating far more than is considered normal. Non-gravitational acceleration refers to any force, other than gravity, that affects an object's trajectory. For comets, this is almost always the result of outgassing, as jets of gas escaping the nucleus act like tiny, unpredictable rocket thrusters. You can model this force, you can predict it, and you can correct for it in your orbital calculations. But with 3I divided by Atlas, the corrections keep changing. Each new batch of observational data requires a significant tweaking of the model. While this is not entirely unheard of for highly active comets, the sheer magnitude and inconsistency of the changes are raising eyebrows among the professionals who track these objects for a living. Some of these researchers have noted, in private forums and email chains, that the object's light curve, the plot of how much light it reflects over time, does not conform to standard models of ice sublimation. It is highly irregular, almost pulsed, as if the outgassing is occurring in controlled, staccato bursts rather than as a steady, continuous process. This behavior could be natural, perhaps driven by the object's rotation exposing localized, highly active regions on its nucleus to sunlight. Or it could indicate something far more controlled, something more deliberate. Now, let's talk about the timing of information. Because the gaps between observation, analysis, and public disclosure are themselves incredibly revealing. The James Webb Space Telescope captured its game-changing spectroscopic data of 3I divided by Atlas in late September. That data, as we discussed, showed the unusual dominance of carbon dioxide. But the findings were not made public until mid-October, a full 2.5 weeks later. That kind of lag is not, in itself, shocking. The peer review process takes time. Data must be painstakingly verified, calibrated, and interpreted. But in the past, major JWST observations of other comets have been shared far more rapidly, sometimes within a matter of days, especially when the findings are exciting and novel. Why the significant delay here? Was it simply an abundance of caution and scientific thoroughness, or was it something else? Was there a review process that extended beyond the usual scientific channels, perhaps into the corridors of security and policy agencies, to deliberate on how best to frame such anomalous findings? There is also the matter of data embargoes, which are standard procedure in astronomy but can be intensely frustrating for those on the outside looking in. When a major observatory captures unique data, The scientific team that proposed the observations is typically granted an exclusive period of access, often 6 months to a year, to analyze the data and publish their findings before the raw information is released to the public. This is a fair system, designed to protect the intellectual investment of researchers. But in a situation like this, it creates an informational black hole. We know the JWST looked at 3I divided by Atlas. We know a host of powerful ground-based telescopes have been tracking it. We know that radar facilities have attempted observations, but we do not know the full scope of what those instruments have seen. We have no idea what secrets are currently sitting in embargoed data archives, awaiting publication or clearance or some other form of institutional approval before they ever reach the public consciousness. And in a situation where public interest is this high and official statements are this carefully limited, that opacity becomes a breeding ground for speculation. Consider the phrasing one more time: no threat to Earth. Why specify Earth? Why not a more encompassing statement like no threat detected or no danger posed? The very specificity of the language implies that someone, somewhere, either asked about or was concerned about threats that are not on a planetary scale. Threats to our infrastructure, perhaps. Our increasing, almost total, reliance on vast satellite constellations for global communications, GPS navigation, financial transactions, and military coordination has created a new class of vulnerabilities. A large solar storm can disrupt these systems. So can a burst of intense cosmic radiation. Could an object like 3I, divided by Atlas, with its highly unusual emissions and high-energy environment, pose a tangible risk to our orbital assets without ever threatening the planet's surface? That is a question that would not have even been relevant 30 years ago. But today, with tens of thousands of satellites planned for low Earth orbit, it is suddenly a question of critical importance. And if our agencies are quietly assessing that very risk, they might logically frame their public statements to avert widespread panic without ever lying about the specific, narrow danger they are actually evaluating. Then there is the regulatory environment to consider. In the United States, certain types of astronomical data can fall under export control regulations, like ITAR, International Traffic in Arms Regulations, if they are deemed to have potential national security implications. If our most advanced sensors detected something about 3I divided by Atlas, anything at all that defense analysts deemed sensitive, the data itself could become a state secret. Not because the object is dangerous, but because the data is informative. It could reveal the true capabilities of our detection systems or our analysis methods. This does not require a shadowy conspiracy. It just requires bureaucrats diligently following established rules designed to protect strategic advantages. The end result, however, is the same: a growing chasm between what the professionals know and what the public is being told, a gap that widens in direct proportion to how unusual the object becomes. The pattern is undeniable and it keeps repeating. We have official statements that are technically accurate but surgically scoped. We have observational data that is either embargoed or mysteriously delayed. We have a level of coordination that is happening behind closed doors, revealed only through anonymous leaks or glaring inconsistencies in the public record. It does not quite rise to the level of a cover-up, because there is no clear, demonstrable evidence of outright deception. But it is certainly not transparency either. It is something in between. A managed narrative where the institutions in control of the information are deciding what the public needs to know and precisely when they need to know it. Perhaps that approach is appropriate. Perhaps there are very good reasons to move slowly, to triple verify findings before broadcasting them, to avoid causing unnecessary global alarm over anomalies that might, in the end, resolve into perfectly mundane explanations. But the cost of that institutional caution is public trust. Every delay, every vague statement, every unanswered question feeds the growing perception that something significant is being withheld. And in an era where institutional trust is already perilously fragile, that perception can become its own kind of crisis, entirely separate from whatever the object itself might actually represent. So here we are, caught in the unnerving space between two parallel realities. The official reality, where 3I divided by Atlas is a fascinating but ultimately harmless comet being studied by cooperative international teams of scientists. And the unofficial one, where our most sophisticated defense systems are quietly engaged, where critical data is being carefully controlled, and where the full story, whatever it may be, will not be told until long after the object has vanished from our skies. Which of these realities is more accurate? The answer is probably both, and probably neither. The truth most likely resides in the uncomfortable, grey space between them, where facts and fears coexist, and where the line separating pure science from national security has blurred beyond all recognition. Part 5. The pattern repeats, from Oumuamua to Atlas. Let's rewind the clock to October 19th, 2017. Astronomers at the University of Hawaii's Pan-STARRS telescope are reviewing images from the previous night's survey when they spot something profoundly odd. A faint, fast-moving streak of light, already past its closest approach to Earth, and clearly on a trajectory heading out of the solar system. Follow-up observations over the next frantic few weeks confirm what initially seemed impossible. The object had come from interstellar space, had passed within a hair's breadth of Earth just 24 million kilometers, and was now departing, never to be seen again. They named it Oumuamua, a Hawaiian word aptly meaning scout, or a messenger from afar arriving first, and with that, the world's first confirmed interstellar visitor became an instant global sensation. But Oumuamua refused to behave. Its shape, inferred from its wild variations in brightness, was extremely elongated, perhaps as much as 10 times longer than it was wide, more like a cosmic needle than a rock. It showed absolutely no signs of cometary activity, no glowing coma, no tail, despite having just passed very close to the sun where any ice should have been vigorously vaporizing. And then, most bizarrely of all, as it receded into the darkness, astronomers detected a slight, anomalous acceleration, a tiny deviation from the trajectory that gravity alone could explain. Comets do this all the time. It's the gentle push of outgassing, but Oumuamua showed no outgassing. So, what was pushing it? A flurry of explanations proliferated. Perhaps it was outgassing pure hydrogen, which would be invisible to our telescopes. Perhaps it was a bizarre fragment of a planet that had been shattered by tidal forces and violently flung into interstellar space. Maybe it was a solid nitrogen iceberg, a chip off a Pluto-like world from a distant star system. Or, as Dr. Avi Loeb provocatively proposed, perhaps it was a light sail, a thin, manufactured object designed to be pushed by starlight, a piece of alien technology, either sent deliberately or the derelict debris of a long-dead civilization. The scientific community, by and large, rejected the artificial hypothesis, strongly favoring the more exotic but still natural explanations. The public, however, was captivated. Here was a true mystery, a tantalizing possibility, the universe seemingly knocking on our front door. The SETI Institute coordinated radio observations, listening intently for any hint of artificial signals. They found nothing. Oumuamua faded back into the blackness of space, and the debate surrounding it faded as well, unresolved, but shelved, waiting for the next visitor to provide more context. That next visitor arrived in August 2019. Gennady Borisov, a Crimean amateur astronomer, detected a new comet with a highly unusual orbit. Further observations quickly confirmed it was interstellar, the second ever detected. They named it 2I divided by Borisov, and unlike Oumuamua, this one behaved exactly as a comet should. It had a vast, glowing coma. It had a prominent tail. Spectroscopic analysis revealed the familiar signatures of water vapor, carbon monoxide, and dust, all the standard ingredients we expect from these icy bodies. Borisov was strange only in the sense that it came from somewhere else. Its behavior was familiar, almost comforting. It seemed to reassure the scientific community that interstellar objects could be normal, that Oumuamua was perhaps the bizarre outlier, not the template. Telescopes worldwide tracked Borisov for months as it swung around the sun and departed. Data flowed freely. Dozens of papers were published. The object provided a crucial baseline, a reference point for what a normal interstellar comet should look like. and then it too faded, leaving us with just 2 data points and an infinite number of questions about what else might be out there. And now we have 3 I divided by Atlas, the 3rd confirmed interstellar visitor in just 8 years. That pace of discovery, in and of itself, is noteworthy. For the entirety of human history, up until 2017, we knew of 0 interstellar objects passing through our solar system. Now, we are averaging 1 every 2.7 years. Part of this is undoubtedly an improvement in our detection capabilities. Our sky surveys have become exponentially more powerful. We are scanning more of the sky, more frequently, and with more sensitive instruments. Objects that would have gone completely unnoticed just a generation ago are now being caught in our digital nets. But there is also the uncomfortable possibility that the rate of visitation hasn't actually changed. We've just finally started noticing. Perhaps interstellar visitors have always been this common, and we are only now, in the 21st century, developing the technological eyes to see them. If that's true, it raises profound questions about what else we have been missing. What else is passing through our system, undetected, because we're not looking in the right places or at the right wavelengths. But let's focus on the emerging pattern, because patterns can reveal underlying structures, and structures suggest a process. Oumuamua was anomalous in its shape, its trajectory, and its acceleration. Borisov was normal in all of those respects, but anomalous purely in its origin. 3I divided by Atlas is anomalous in its composition, its emissions, and, most critically, in the unprecedented official response it is triggering. Each object has been strange in a completely different way. This could simply mean that our sample size is far too small to draw any meaningful conclusions, that we don't yet have a grasp on the true diversity of interstellar objects. But it could also mean that interstellar space is far more varied and complex than our models have ever assumed, that objects arriving from other star systems are carrying the unique chemical and physical signatures of environments we have never studied, shaped by processes we have never witnessed. And if that diversity includes technological artifacts, either functional probes or ancient, inert debris, we would need a much larger sample size to learn how to distinguish natural variation from artificial design. Consider the evolution of our response. When Oumuamua arrived, the scientific community scrambled to observe it, but there was no centrally coordinated mobilization. It was a response driven by excitement, not by protocol. Observatories pointed their instruments at it because individual researchers wanted to, not because a global agency directed them to. By the time Borisov appeared, there was slightly more structure. SETI coordinated its listening campaigns more formally. NASA issued more structured statements. But the response still felt reactive, opportunistic. 3I divided by Atlas is different. The response is proactive, highly structured, almost as if it were rehearsed. The IAWN launched its global campaign before the object's perihelion, giving teams around the world time to prepare, to allocate precious resources, and to coordinate their observation schedules. This evolution from ad hoc curiosity to institutionalized mobilization reflects a fundamental shift in how we are beginning to treat these objects. We have moved from studying them as mere scientific novelties to treating them as significant global events that require management, coordination, and perhaps even contingency planning. Is there an emerging, classified protocol for these events? Did the profound lessons learned from Oumuamua and Borisov lead to a series of internal discussions, classified policy papers, and recommended procedures for handling future interstellar detections? If so, those documents would almost certainly remain internal, circulating only among agency heads, defense liaisons, and key international partners. We may never see them, but their existence would perfectly explain the current state of readiness, the speed with which the IAWN mobilized its campaign, and the apparent ease with which strategic defense assets were reportedly retasked. It would mean that somewhere, in the quiet, bureaucratic machinery that operates far from public scrutiny, someone anticipated this. Someone planned for the next interstellar visitor and built the institutional frameworks to respond. Whether that planning was driven by pure scientific interest, by pressing defense concerns, or by a mixture of both, is the question we cannot yet answer. The public's perception has also shifted dramatically since Oumuamua. Back in 2017, the alien probe theory was largely considered fringe, confined to tabloids and speculative corners of the internet. By the time of Borisov in 2019, it had entered mainstream discourse, being debated seriously on news programs and in academic panels. Now, in 2025, it is almost an expected part of the conversation. When 3I divided by Atlas was announced, one of the very first questions asked by mainstream journalists was whether it could be artificial, not whether it was dangerous or what we might learn from it, but whether it was a spacecraft. This shift reflects broader cultural currents, a growing public openness to the possibility of extraterrestrial technology, driven in part by recent government disclosures regarding unidentified aerial phenomena, UAPs, and the increasing legitimization of SETI research by mainstream institutions. The public is primed for this conversation in ways they simply were not a decade ago, and that priming creates a new kind of pressure on our agencies to address the question, even if the answer is deeply uncertain. So, here is the pattern. Each interstellar visitor has been profoundly anomalous in some way. Each has triggered an escalating level of organized, institutional response. Each has raised fundamental questions that outlast the object's brief passage through our skies. And each time, the gap between what we observe and what we understand grows a little bit wider, while the gap between public curiosity and official disclosure becomes a little more uncomfortable. We are building a catalogue of the strange, 3 objects and counting, with no clear framework for interpreting what they mean collectively. Are they emissaries from a galaxy that is far more active and populated than we have ever dared to imagine? Are they just random pieces of cosmic shrapnel from distant stellar collisions that happen to be passing through our neighborhood? Or are they evidence of something intentional? Probes, or messages, or perhaps ancient markers left by civilizations that rose and fell while the Earth was still a molten ball of rock? We don't know, but we are learning to expect them. And that expectation, that new state of readiness to encounter the unexpected, is fundamentally changing how we watch the sky. We are no longer just passive observers. We are becoming active interrogators, pointing our most powerful instruments not just to record what is there, but to question what it might be. 3I divided by Atlas is the latest test of that evolving stance. And depending on what we find or what we are eventually told has been found, it may not be the last. The universe has a way of repeating its lessons until we finally learn them. Perhaps the lesson here is that we are not alone in our strangeness, that the cosmos is filled with things that defy our neat little categories, that the line between the natural and the artificial begins to blur the farther from home you look. Or perhaps the lesson is simpler and far more humbling, that we are still just beginners, students of a universe far more complex and mysterious than our models will ever allow. And the only way forward is to keep watching, keep questioning, and keep having the courage to admit when we simply do not have the answers. 3I divided by Atlas will leave, the next object will arrive, and each time we will be a little more ready, a little more uncertain, and perhaps a little closer to understanding what it truly means to live in a galaxy that occasionally sends visitors to our door. Part 6. The Nickel Code. Alien signature or exotic chemistry. Let's talk about the nickel, because this is the precise point where mundane chemistry evaporates into profound mystery, and where rigorous science begins to sound uncannily like espionage. Nickel is element number 28 on the periodic table. It is a silvery white, lustrous metal, a common component of the Earth's core, of stainless steel, and of the rechargeable batteries that power our lives. It is, in a cosmic sense, everywhere, forged in the thermonuclear hearts of massive, dying stars and scattered across the galaxy by supernova explosions. Nickel is one of the fundamental building blocks of rocky planets and metallic asteroids. We fully expect to find it in comets, but locked away inside dust grains, chemically bonded with iron in roughly the same proportions we see in our own Sunday. What we do not expect, what we have never before witnessed, is to see it outgassing as a free, neutral atomic vapor, glowing with its own distinct spectral lines, divorced from its usual elemental companions. And we absolutely, under no circumstances, expect to see it without a corresponding signature of iron, its ubiquitous chemical twin, the element from which it is almost never separated in any known natural cosmic process. But that is exactly what the Keck Observatory detected in mid-October. The observations came from the Keck Cosmic Web Imager, KCWI, a state-of-the-art instrument capable of capturing incredibly high-resolution spectra across the visible light spectrum. When you pass light through a prism or a diffraction grating, it splits into a rainbow, and within that rainbow, you find a series of dark or bright lines, a unique, unmistakable spectral fingerprint that corresponds to specific atoms and molecules absorbing or emitting light at precise energies. The KCWI data showed distinct emission lines at 352 and 341 nanometers, the specific wavelengths associated with neutral nickel atoms, not nickel ions, which would suggest a high-temperature plasma environment, but neutral atoms, which implies a cooler, more controlled environment where electrons haven't been stripped away. That distinction is critical, because neutral nickel emission requires a very specific set of conditions. Enough energy to vaporize the nickel from its solid form, but not so much energy that it becomes ionized. It is a chemical Goldilocks zone, and to find it existing within the chaotic coma of a comet is bizarre. The complete absence of iron makes the finding exponentially stranger. In meteorites, in asteroids, in the Sun itself, the nickel-to-iron ratio is a well-established constant, roughly 1 to 20 by mass. They are smelted together in stellar cores, mixed together during planetary formation, and remain chemically coupled through almost all geological and cosmic processes. To separate them requires fractionation, a process that preferentially extracts one element over another, and that typically involves industrial-level chemistry that simply does not happen naturally on the cold, radiation-blasted surface of a comet. On Earth, we fractionate nickel all the time, using highly controlled industrial processes, like the Mond process. We heat nickel-bearing ores and react them with carbon monoxide under high pressure to form nickel tetracarbonyl, a highly toxic and volatile gas. This gas can then be decomposed elsewhere to yield almost pure nickel. It is how we refine the metal for our most demanding commercial uses. But Earth has factories. It has contained environments and intentional engineered chemistry. Comets are not supposed to. The nickel tetracarbonyl hypothesis emerged almost immediately after the Keck data was unofficially circulated among experts. If the coma of 3I divided by Atlas is indeed rich in carbon monoxide, which spectroscopy has confirmed, and if temperatures and pressures in localized regions near the nucleus could somehow create the right conditions, it is theoretically possible that nickel from the comet's dust grains could react to form nickel tetracarbonyl. This compound is extremely volatile, meaning it would vaporize easily, and it is known to break down when exposed to ultraviolet radiation, which would release the neutral nickel atoms that then emit the light we observe. It is a plausible chemical mechanism. Chemistry textbooks describe it. We have been synthesizing it in laboratories for over a century, but we have never, ever detected it in a comet. We've never even had a reason to think a comet could produce it. The required conditions, moderate pressures and temperatures within a carbon monoxide-rich environment, are simply not typical of comet surfaces, which are generally near-perfect vacuums exposed to the harsh solar wind. So, either 3I divided by Atlas is somehow providing these unique conditions through some unknown internal process, or the nickel is being released by a completely different mechanism. Let's explore the natural hypotheses first, because the scientific method demands that we exhaust all conventional explanations before we even consider invoking extraordinary ones. Could the nucleus of 3I divided by Atlas contain unusually nickel-rich grains, perhaps metallic inclusions that were formed in a completely different type of protoplanetary disk under chemical conditions alien to our own? Yes, that is conceivable. Stellar systems with a higher metallicity, more heavy elements than our Sun could produce dust and ice mixtures, unlike anything found in our own solar system's comet populations. If 3I divided by Atlas was born around such a star, Its composition might simply reflect that exotic origin, but this still doesn't fully explain the absence of iron. It would require a secondary process of fractionation, a specific mineralogy where iron is somehow sequestered in non-volatile compounds, while nickel is free to escape preferentially. It's possible, but it adds another layer of special pleading, another low-probability event. Now, let us dare to entertain the uncomfortable possibility, the one that makes some scientists cringe in their seats and others lean forward with intense curiosity. What if the nickel emission is not natural at all? What if it is technological residue, the exhaust or effluent of processes that were never meant to be natural? This doesn't require us to believe that 3I divided by Atlas is a piloted spacecraft. It could be an ancient probe, millions of years old, dormant and slowly decaying. Its outer layers could be ablating as it nears our sun, releasing materials that were processed by technologies we cannot yet imagine. It could be the inert debris from some vast industrial process that occurred in interstellar space long ago, the waste material ejected from a long-dead civilization's refining operations, drifting through the galaxy for eons until it happened to pass through our solar system. The point is, if we allow for the possibility that intelligence exists elsewhere, and has existed for cosmological timescales, then its artifacts, whether intentional or incidental, might look exactly like this. They would present as objects with anomalous compositions, unexpected emissions, and a chemistry that requires either incredibly convoluted natural explanations or elegantly simple artificial ones. Dr. Avi Loeb has been particularly vocal on this point, arguing that the scientific method itself demands we consider all hypotheses that are consistent with the data, rank them by their plausibility, and then test them rigorously, rather than preemptively dismissing some based on philosophical discomfort. His position is not that 3I divided by Atlas is definitely artificial. It is that we must conduct the specific observations necessary to either rule that possibility in or out, and that failing to do so because we are afraid of the potential answer is simply bad science. Regardless of the debate, the nickel mystery feels like a threshold. It is specific enough to be testable, strange enough to be provocative, and ambiguous enough to sustain multiple, competing interpretations. Whether it is a sign of exotic interstellar chemistry or something genuinely artificial, it represents a profound challenge to our understanding. It is a stark reminder that the universe contains more mechanisms than we have catalogued, and more possibilities than our current models can encompass. And perhaps that is the real signature here, not necessarily of aliens, but of our own ignorance, of the vast, humbling gap between what we know and what is knowable. The nickel code, as some have begun to call it, might eventually be decoded into something mundane, or it might crack open a chapter in human history for which we are profoundly unprepared. Either way, ignoring it is no longer an option. The anomaly is real, and the only way forward is to keep digging. Part 7. The Hidden Campaign. Are astronomers being silenced? Silence is not always indicative of a conspiracy. Sometimes it is simply procedure. It is the sound of institutional caution, the slow, grinding machinery of scientific consensus being built behind closed doors. But when that silence coincides with profound anomaly, when data that should be flowing freely suddenly stops, when researchers who should be rushing to publish their findings are conspicuously quiet, people begin to notice, and they begin to wonder. In the weeks since 3I divided by Atlas became headline news, a quiet but persistent chorus of concern has emerged from the global community of amateur astronomers, from the dedicated users of online forums who meticulously track orbital elements, from the people who watch the watchers and have noticed that something feels distinctly off. The data stream, they claim, has become inconsistent. Public updates from the Minor Planet Center, which should be appearing daily for an object of this interest, are now appearing only every few days. Key orbital parameters that should be converging, that is, becoming more precise as more observations are added, are instead fluctuating in ways that suggest either the data being submitted is very noisy or that it is being very selectively reported. Some dedicated users on astronomy subreddits have compiled detailed tables comparing the public databases, the MPC listings, versus JPL's Horizons system, versus international ephemeris services, and have found small but significant discrepancies. We are talking about fractions of an arcsecond in position, hundredths of an astronomical unit in distance. But they are discrepancies nonetheless. They are just enough to suggest that not everyone is working from the same complete dataset, or that some data is being deliberately held back from public release. Now, to be perfectly clear, this is currently speculation. These are unverified claims from people who are not official insiders, who do not have access to the institutional data pipelines. It is entirely possible they are misinterpreting normal statistical variations, seeing patterns in random noise, or simply overestimating how quickly data should propagate through complex systems that were never designed for instantaneous, real-time updates. Astronomy databases have inherent latency, but the sheer volume of this speculation, the growing number of independent, expert voices all raising the same concerns, suggests that something feels fundamentally wrong to the very people who have been watching these systems operate for years. They know what normal data flow looks like. This, they claim, does not feel normal. The standard practice of data embargoes adds another layer of opacity. When a research team uses a major facility like the JWST or the Hubble Space Telescope, they are granted a proprietary period, as we've discussed. This system works well for the slow, deliberate pace of most scientific discovery, but it creates an informational fog during a fast-moving event that has captured the public's intense interest. If a team has embargoed data that shows something truly extraordinary about 3I divided by Atlas, we, the public, may not know what that data contains until months after the object has faded from view. Whatever secrets it might reveal will be old news by the time they are finally disclosed, analyzed in retrospect rather than being used to guide real-time decisions and public discourse. There is also the very real possibility of informal delays, of quiet requests from coordinating bodies or even government liaisons that certain sensitive findings be held pending further review. This is not necessarily censorship in the authoritarian sense. It is institutional risk management. If an observation suggests something genuinely unprecedented, something that might require a coordinated policy response or even diplomatic consultations, releasing that information prematurely could create widespread confusion, panic, or geopolitical complications. Imagine a hypothetical scenario. A researcher detects a faint but structured modulated radio signal emanating from 3I divided by Atlas. Do they immediately tweet about it and post a preprint paper online? Or do they contact their institution's security office, quietly notify NASA or ESA, and wait for official guidance on how to proceed with disclosure? Almost any responsible scientist would choose the latter path, not because they are being actively silenced, but because they recognize the profound implications of their discovery and want to handle it with the utmost responsibility. But from the outside, that responsible delay looks identical to suppression. It looks like scientists being muzzled by shadowy authorities. The perception and the reality diverge, and in that gap, conspiracy theories are born and thrive. The very structure of the IAWN campaign adds another potential filter. Participation is not open. It requires registration and vetting. This is reasonable for quality control, but it also creates a gatekeeper dynamic. Who decides which observational teams are credible? And once accepted into the campaign, are participants bound by any non-disclosure agreements regarding the timing of their publications? The secretive workshop scheduled for late November will likely serve as the main coordination point, the moment where all the disparate results are compiled, cross-checked, and packaged for a unified public release. But until that workshop happens, individual researchers may be strongly discouraged from publishing their own preliminary, uncorroborated results. Again, this isn't necessarily a conspiracy, it's just a process of coordination. But the practical effect is the same, a period of informational drought for the public, while a select group of insiders analyzes data the rest of us are not permitted to see. If there is a hidden campaign, it is likely not a single, monolithic conspiracy to deceive. It is more likely an emergent property of complex, 20th century institutions trying to manage a 21st century problem in real time. It is what happens when the speed of global information flow clashes with the deliberate, cautious pace of institutional science. when an interconnected global society demands answers faster than the evidence can responsibly provide them. 3. I, divided by Atlas, has arrived at a moment of maximum tension between these forces, and what we are witnessing is the system straining to adapt, creating a silence that is as baffling and provocative as the object itself. Part 8. Testing the Shield. Is 3I divided by Atlas a planetary defense drill? Let us now state the hypothesis plainly, because dancing around it with cautious language serves no one. What if 3I divided by Atlas is not just being observed, but is being actively used? Not as a threat, but as a target. A live, high-fidelity exercise to test whether the vast, multi-billion-dollar planetary defense infrastructure we have painstakingly built over the past decade can actually function under real-world conditions, with real-time pressure, and with a cascade of genuine, unscripted unknowns. It is an uncomfortable idea, because it implies that our global agencies are conducting a major readiness drill without telling the public, treating an actual celestial event as a convenient training opportunity. But from a strategic standpoint, it is also ruthlessly pragmatic. You do not construct a complex, globe-spanning system to protect the Earth from cosmic hazards and then simply wait for an actual, confirmed threat to see if it works. You test it. You test it relentlessly with simulations, with tabletop exercises, and when a perfect, low-risk opportunity presents itself with a real object that poses no intrinsic danger, but exhibits all the challenging characteristics you need to practice, detecting, tracking, and characterizing. The timing of this event strongly supports this hypothesis. The IAWN's astrometry campaign was announced in mid-October, less than 2 weeks before perihelion, the precise moment when 3I divided by Atlas would be at its closest to the Sun, at its most active, and at its most scientifically interesting. That is an incredibly tight turnaround. Normally, major coordinated observation campaigns are planned months, if not years, in advance, giving research teams ample time to compete for precious telescope access, write detailed proposals, and secure the necessary funding. This one materialized with the speed of an emergency response, suggesting either an exceptional, unstated urgency or the activation of pre-existing contingency plans that were simply waiting for the right trigger. The very structure of the campaign, with its stringent registration requirements and its intense emphasis on data standardization, perfectly mirrors the protocols developed for tracking high-risk near-Earth objects. In those scenarios, precision is paramount, because tiny errors in orbital prediction can mean the difference between a safe passage and a catastrophic impact. But 3I divided by Atlas carries no impact risk. Its orbit is well determined. So why the obsessive emphasis on precision? What exactly are they trying to calibrate against? Recall the phrase used in the New York Post article, interplanetary defense system deployed. That is potent language. Deployment is a term drawn from the lexicon of military operations, signifying a system transitioning from a passive, standby state to an active, operational one. None of them explicitly address protocols for interstellar visitors or for hazards that are non-kinetic in nature. But the absence of public documentation does not mean the absence of protocols. Government agencies, particularly defense and intelligence agencies, develop contingency plans for a vast range of scenarios they have no intention of publicizing, classified annexes, internal guidelines, and decision trees that remain entirely obscure until the moment they are invoked. Consider what a comprehensive planetary defense drill would aim to test. First, detection and sensitivity. Can our global network of survey telescopes reliably identify an object with highly unusual characteristics, flag it for immediate follow-up, and disseminate those findings quickly enough to coordinate a global response? 3I divided by Atlas was discovered by the Atlas survey, a system designed for NEOs, but its interstellar nature was confirmed within days. That represents a baseline success. But were other, more sensitive systems tracking it before the public announcement? Did classified sensors detect it independently and then cross-reference their findings with civilian data? That kind of seamless integration, the blending of open-source astronomy with secured, military-grade observation platforms is the holy grail for achieving comprehensive situational awareness. Testing it requires a real, unpredictable target, and 3i divided by atlas provided the perfect one. Second, characterization and accuracy. Once a novel object is detected, how rapidly and accurately can we determine its fundamental properties, its size, its composition, its precise trajectory, and any potential hazards it might pose? For an impact scenario, this is straightforward. But for an anomalous object, the task is far more complex. It means identifying any and all deviations from expected behavior, unusual emissions, trajectory perturbations, anything that suggests the object is not what it initially appears to be. The IAWN campaign's intense focus on astrometry hyper-precise position measurements fits this goal perfectly. If the object were to exhibit any non-gravitational acceleration beyond what cometary outgassing models could predict, precise astrometry would be the very first indicator. Catching that subtle deviation would be a powerful demonstration of the system's readiness. Third, communication and protocols. Can critical information flow smoothly and securely between civilian researchers, institutional administrators, government liaisons, and international partners? A drill would be designed to stress test those very channels under realistic conditions. Did the Minor Planet Center coordinate flawlessly with NASA's Planetary Defense Coordination Office? Did NASA communicate effectively with the European Space Agency and other spacefaring nations? Did our classified observation networks share their findings with civilian analysts, and vice versa? The smooth, seemingly effortless coordination evident in the IAWN campaign suggests a well-oiled machine, the product of procedures that have either been extensively practiced or, at the very least, meticulously documented on paper. Fourth, and most critically, decision-making and thresholds. At what precise point does passive observation transition into active response? For impact threats, that threshold is relatively clear. But for non-impact anomalies, the threshold is far murkier. If an object begins to exhibit behavior that suggests it might be artificial, who makes that call? What level of evidence would be considered sufficient? And what actions would follow such a determination? A drill scenario would allow agencies to walk through these incredibly sensitive decision trees, to identify bureaucratic bottlenecks, and to refine their protocols for future use, all without having to trigger actual mitigation efforts. 3i, divided by Atlas, with its deeply ambiguous characteristics, is the ideal subject for this. It is strange enough to prompt a serious consideration of non-natural hypotheses, but safe enough that exploring those hypotheses doesn't require immediate, panicked action. It is a thought experiment made real. The counter-argument, of course, is why use a real object at all? Simulations are cheaper, easier, and fully controllable, but simulations have profound limits. They don't test whether your telescopes can actually detect a faint, anomalous signal through the noise of a real sky. They don't stress your communication networks with the uncertainty and ambiguity of real data. And they don't reveal the subtle gaps in coordination that only appear when multiple, independent institutions with different cultures and competing priorities are forced to work together against a ticking clock. A real-world exercise provides a level of validation that simulations simply cannot. There are, however, significant ethical implications. If our agencies are using 3i divided by Atlas as a test case, without disclosing that intention, they are essentially treating the global public as unwitting participants in their exercise. The information that is released, the language that is used, the timing of the official statements, all of it becomes part of the test, a way of gauging how public perception responds to managed messaging. That is a form of manipulation, even if it is well-intentioned. It denies people the ability to critically evaluate the situation for themselves. It turns transparency into a variable to be tested rather than a value to be upheld. And once that trust is compromised, it is incredibly difficult to rebuild. The next object, the next anomaly, will be met with a default posture of skepticism, with the widespread assumption that our agencies are once again withholding the full context. But here is the uncomfortable truth. Planetary defense, by its very nature, exists at the volatile intersection of science and national security. And that intersection is inherently, unavoidably ambiguous. The culture of science demands openness, peer review, and vigorous debate. The culture of security demands control, verification, and the ability to act decisively without telegraphing capabilities. Bridging those two worlds requires compromise. Sometimes that means delays. Sometimes it means partial disclosure. And sometimes it may mean conducting critical readiness tests without full public awareness. If 3I divided by Atlas is indeed a drill, we will likely never receive an official confirmation. Agencies do not typically advertise their internal exercises until long after they have been concluded and all the lessons have been learned. By the time any official acknowledgement might emerge, if it ever does, the object will be gone. What we will be left with are the hints, the circumstantial evidence, and the patterns visible only to those who watch carefully. And perhaps that is enough. Perhaps the point isn't to definitively prove that this was a test, but to recognize that the discipline of planetary defense has now matured to the point where it can conduct such a test. The infrastructure now exists to respond to ambiguous threats in a highly coordinated, multi-layered fashion. A world where the line between scientific observation and strategic operation has blurred beyond recognition. We are watching a system that operates in both modes simultaneously. Scientific and strategic, open and guarded, collaborative and compartmentalized. And that system, whether we trust it or not, is now active in a way it simply was not a decade ago. 3I divided by Atlas did not create this new reality, but its arrival has made it visible to us all. If that reporting was accurate, it suggests that a predefined, classified protocol was triggered, that someone in a position of authority determined that this specific object met the criteria for an elevated, non-standard response. What were those criteria? We don't know. The publicly available documents that describe the IAWN's role in planetary defense are focused on near-Earth object monitoring, asteroid deflection technologies, and impact warning procedures. Part 9. The Alien Hypothesis Revisited. Let us now confront the question directly, because studiously avoiding it has not made it go away. Could 3I divided by Atlas be artificial? Not as a certainty, not as a proven fact, but as a legitimate possibility. And more importantly, what would it mean methodologically, philosophically, and practically if we were to take that possibility seriously, instead of reflexively dismissing it as the domain of fantasy? The alien hypothesis, as it is often called with a mixture of public fascination and academic derision, has been the silent, shadowy companion to every interstellar object we have detected. With Oumuamua, the suspicion was sparked by its improbable shape, its anomalous acceleration, and its utter lack of cometary features. With Borisov, it was simply its origin, the mere fact of its arrival from the void. With 3I divided by Atlas, it is the cascade of anomalies, the bizarre composition, the inexplicable emissions, the hyper-accelerated official response, all of which feed the growing speculation that we are looking at something engineered, something intentional, perhaps even something still functional. Let's begin by revisiting the data points that make purely natural explanations so awkward. The carbon dioxide to water ratio of 8:1 is, as we've established, chemically possible but statistically very, very unusual. Most comets are formed in environments where water ice is dominant, simply because hydrogen and oxygen are the first and third most abundant elements in the cosmos. An object so heavily dominated by carbon dioxide suggests it was formed in a very particular, very cold, and likely carbon-rich niche of some distant protoplanetary disk. It is possible, yes, but you must then multiply that low probability by all the other anomalies. The emission of nickel without its chemical twin, iron, the extreme negative polarization of the light reflecting from its dust, the incredibly early and energetic outgassing, the statistically improbable alignment of its trajectory with our solar system's ecliptic plane. Individually, each of these oddities has a potential, albeit sometimes strained, natural explanation. Collectively, however, they begin to strain credulity. This is where a form of reasoning known as Bayesian inference becomes a powerful tool. In simple terms, you are weighing the combined probability of multiple, independent, rare, natural events, all happening to coincide in a single object, against the probability of a single, unifying artificial explanation. If you assign the artificial hypothesis a prior probability of 0, a philosophical stance that some scientists effectively take, then no amount of anomalous evidence will ever be enough to shift that assessment. But if you allow for even a tiny, non-zero prior probability for the existence of extraterrestrial technology, then the sheer accumulation of so many anomalies in one place starts to make the artificial hypothesis look statistically competitive with the increasingly contrived natural ones. Now, let's talk again about non-gravitational acceleration, because this is where Oumuamua set a critical precedent. Comets exhibit this routinely through outgassing. The jets of gas act as tiny thrusters, altering the trajectory in ways that are generally predictable. For Oumuamua, the measured acceleration came with no visible outgassing, which led to a host of creative explanations, from invisible hydrogen ice to the gentle push of solar radiation pressure on a very thin, flat object. For 3, I divided by Atlas. If similar anomalous accelerations are detected, we would expect them to correlate with its observed cometary activity with the pulses in its brightness and its documented gas emissions. But what if they don't? What if the object is observed to accelerate, or, even more strangely, decelerate at moments that are completely unrelated to its proximity to the Sun? What if it makes trajectory adjustments in directions that do not align with the expected vectors of outgassing? That would be extraordinarily difficult to explain naturally. It would strongly suggest some kind of internal process, either the venting of exotic, unknown volatiles with highly unusual sublimation properties or, far more provocatively, a form of active guidance or attitude control, something adjusting the object's path. This is a domain where machine learning and artificial intelligence are now being applied to trajectory analysis, capable of spotting subtle patterns that human intuition might easily miss. Sophisticated algorithms can detect faint periodicities in an object's light curve, find hidden correlations between brightness fluctuations and positional changes, and identify anomalies in how an object tumbles or rotates. If applied to the full, high-cadence data set for 3i, divided by Atlas, these tools might reveal a hidden structure within the noise, signatures that suggest non-random, controlled behavior. The challenge, of course, is that we are trying to define what random looks like for a class of object we have never seen before. And this brings us to the statistical elephant in the room. 3 confirmed interstellar objects in just 8 years. If you extrapolate that detection rate, it suggests that dozens, perhaps hundreds, of such objects could be passing through our solar system every single year, most of them simply too faint or too distant for our current surveys to detect. Is that plausible? Yes. Astrophysical models of star formation and planetary system evolution do predict that interstellar space should be filled with a vast number of ejected planetesimals, objects flung out of their home systems during the chaotic dance of planetary migration. But here is the twist. If even a tiny fraction of 1% of those objects were not natural, but were in fact artificial probes sent out by countless civilizations exploring the galaxy over millions or even billions of years, then our solar system should be swimming in them. The galaxy is ancient, over 13 billion years old. Technological civilizations, if they exist and if they are exploratory by nature, would have had more than enough time to send probes, perhaps self-replicating ones, to every corner of the Milky Way. The famous Fermi paradox asks, if aliens are common, where is everybody? One possible answer might be, they are here, we're just calling them comets. That is speculation, of course. It is the kind of speculation that makes cautious, conservative scientists profoundly uncomfortable. But it is grounded in a real calculation, a cousin of the famous Drake equation. If a civilization were to launch a wave of self-replicating probes, the number of probes would grow exponentially. Even with very conservative assumptions, the galaxy could be saturated with these devices, some active, some dormant, some derelict, all silently observing or simply decaying. The vast majority would be ancient, their creators perhaps long extinct, their original purposes forgotten. They would drift through star systems, appearing for all intents and purposes like natural objects, unless and until they were examined with extraordinary scrutiny. 3. I, divided by Atlas, could be one of those, a technological relic, a piece of cosmic archaeology, noticed by us only because our own technological capabilities have finally reached the threshold required to see it. The fact is, we have reached a point where the alien hypothesis is no longer exclusively the domain of science fiction. It is uncomfortable, yes. It requires us to make assumptions we cannot yet fully test. But it is also a logical consequence of the age and scale of the galaxy, and a plausible, if unproven, solution to the Fermi paradox. Treating it as a legitimate scientific question is the mature response. This does not mean we should leap to the conclusion that 3I divided by Atlas is a probe. It means we must accept that we do not know, that the current data permits multiple, competing interpretations, and that exploring all of them with equal scientific rigor is how progress is made. The universe has surprised us before. It will certainly surprise us again. And if one of those surprises turns out to be definitive evidence that we are not the first, not the only, and perhaps not even the most successful technological species this galaxy has ever hosted, then the real question becomes, are we ready for that answer? Not technologically, we have built the telescopes and trained the algorithms, but are we ready psychologically, culturally, and institutionally? Are we prepared to integrate the existence of others, even extinct, distant others, into our fundamental understanding of reality? 3I divided by Atlas, whatever its ultimate nature, is giving us a dress rehearsal. It is giving us a chance to practice what it feels like to seriously consider this profound possibility, to live with an uncertainty that touches the deepest questions about our place in the cosmos. In the end, whether the object is natural or artificial, matters less than whether we, as a species, can handle not knowing. Can we resist the powerful human urge to force a premature conclusion, and instead sit with the discomfort of maybe long enough to let the evidence, and only the evidence, guide us toward the truth? That is the real test. Not whether we can detect aliens, but whether we can think clearly and rationally when the possibility of them stares back at us from our own data, daring us to either look away or lean in. Part 10. The Outer Meaning, Cosmic Awareness, and the Great Filter. Let us now take a final step back. Step back from the nickel lines, the orbital elements, and the cryptic protocol names, and dare to ask a much larger question. What does it fundamentally mean that we, as a species, have built planetary defense systems at all? What does it say about humanity in the year 2025 that we now scan the sky relentlessly, that we track thousands of objects in a vast digital catalogue, and that we coordinate on a global scale to watch for threats that most people will never see or even comprehend? It means we have crossed a monumental threshold in our own evolution. We have become a species that is consciously, actively aware of its cosmic context. We are aware of our profound vulnerability and simultaneously of our emerging agency. We have finally understood, on an institutional level, that the universe that birthed us can also extinguish us, but that we might be able to do something about it. This awareness is astonishingly new. For the vast majority of human history, celestial events were either ignored or interpreted through the lens of myth and superstition. Comets were not objects of ice and rock. They were divine omens, harbingers of war, famine, or the death of kings. Meteors were not space debris. They were signs from the gods. Eclipses were terrifying events to be appeased with prayer and sacrifice. The very idea that we could one day understand these phenomena, that we could predict them, and that we might eventually protect ourselves from them would have seemed like the ultimate hubris, an absurd fantasy. Now, it is official government policy. Now, we allocate national budgets for it, we train specialists for it, we build a global infrastructure around it. And that psychological shift from being passive subjects of cosmic whim to becoming active defenders of our own world is one of the most profound and underappreciated transformations in the history of our species. 3I divided by Atlas, whatever its true nature, has become a mirror. It is reflecting back at us the state of our own civilization. It reflects our readiness, our deepest fears, and the foundational assumptions we make about what is out there and what it all means for us. The object itself is indifferent. It has no awareness of our existence. It does not care whether we label it a comet or a probe, whether we study it with fervor or ignore it completely. But our response, the secret mobilization, the public speculation, the tense dance between institutional secrecy and public transparency that is all about us, that is the signature of humanity grappling, for the first time in a truly operational way, with the full implications of being a technological species in a universe that might contain others, or their remnants, or simply dangers we are only now beginning to catalogue. And in that grappling, we are defining ourselves. We are choosing what kind of civilization we want to be when the cosmos truly knocks on our door. There is a concept from the study of existential risk called the Great Filter. It is a theoretical attempt to explain the Fermi paradox. If intelligent life is common, where is everybody? The Great Filter hypothesis suggests that there is some stage in the development of life or civilization that is incredibly difficult to pass, a filter that eliminates almost every species that reaches it. Perhaps that filter is the jump from single-celled to multicellular life. Perhaps it is the development of technology without the corresponding wisdom to use it safely. Or perhaps it is something still ahead of us, a challenge we have not yet encountered, one that typically wipes out civilizations before they have a chance to spread across the galaxy. The question that haunts researchers is, where, in this long chain of cosmic challenges, is the filter? Are we past it, making us the rare survivors of a series of improbable evolutionary hurdles? Or are we approaching it, heading blindly towards some great crisis that will determine whether we persist or perish? Planetary defense might be an essential part of navigating that filter. Not the whole answer, but a critical component. A civilization that cannot protect itself from asteroid impacts will not last long on cosmic timescales. The Earth is struck by objects large enough to cause mass extinctions every few tens of millions of years. If you do not develop the technology to detect and deflect those threats, your evolutionary clock is ticking. Eventually, one gets you. But defense against rocks is just the beginning. The Great Filter might not be a single event, but a whole series of challenges, each requiring a new level of awareness, coordination, and technological competence to overcome. 3. I divided by Atlas, by triggering our planetary defense systems, is essentially giving us a pop quiz from the universe. The stakes are low, because the object itself is harmless, but the test is revealing because our response shows exactly how ready we are for future, higher-stakes scenarios. The cultural impact is harder to quantify, but equally important. The conspiracy theories swirling around 3I divided by Atlas have flourished for one simple reason. The official statements feel incomplete and inadequate. People can sense the gap between what they are being told and what they suspect is actually happening. That gap breeds new narratives, some wild, some thoughtful, but all attempting to make sense of an information vacuum. In an era where trust in our institutions is already at a historic low, this dynamic is not just unfortunate, it is dangerous. It signals a critical weakness, a potential failure point for our civilization. Can we handle the truth, even if it is uncomfortable and uncertain? So what is the outer meaning, the ultimate philosophical takeaway from this moment? Perhaps it is this. We are living through the transition from a species that simply discovers the universe to one that must interact with it defensively, strategically, and with profound caution. We are not just observers anymore. We are participants. We are players in a cosmic game whose rules we are still desperately trying to learn. 3I divided by Atlas, regardless of its nature, marks a pivotal point on that trajectory. A moment where our newfound readiness met its first real, ambiguous opportunity, and we responded with all the tools and all the instincts that we have so far developed. Whether those tools are adequate, and whether those instincts will serve us well, only time will tell. But the fact that we responded at all, that we mobilized globally, that we coordinated observations, that we debated hypotheses, and that we treated an interstellar visitor as something deserving of our most serious attention, that, in itself, is progress. It is the kind of progress that might just help us survive the Great Filter, whatever it turns out to be. Because survival, at cosmic scales, is not about avoiding every threat. It is about building systems that are resilient enough to handle the unexpected, cultures that are wise enough to learn from ambiguity, and institutions that are trustworthy enough to guide us through those terrifying moments when the answers are not clear and the stakes feel infinite. We are not there yet, but we are trying. And 3 divided by Atlas, tumbling through the darkness, unknowing and uncaring, has given us a chance to practice, a chance to rehearse the vigilance and the wisdom we will surely need when the next visitor arrives, and the next, and the one after that, until the question is no longer whether we are ready, but whether we have finally become the kind of species that can look out at the vast, mysterious universe and see not just beauty or danger, but opportunity, challenge, and the faint, distant reflection of our own highest aspirations staring back. Part 11. The Quantum Observatory Awakens. Now, we must shift our focus, because while 3 divided by Atlas has dominated the headlines, something else of potentially even greater significance has been unfolding in the deep background, largely unnoticed. It is a technological leap that might be poised to redefine not just this event, but how we observe the universe altogether. In September 2025, fragmented reports began to emerge from China regarding a prototype quantum telescope, designated Tianlong-1 or Sky Dragon-1. The system allegedly achieved first light in a series of highly controlled, classified tests. The details remain exceptionally sparse, filtered through the opaque lens of state-controlled media and a handful of technical papers that raise far more questions than they answer. But the core claim is nothing short of revolutionary. The successful use of quantum entanglement to dramatically enhance imaging resolution and signal detection capabilities, far beyond the theoretical limits of classical optics. If this is true, and that is a monumental, if it represents the kind of breakthrough that doesn't just incrementally improve existing capabilities, but opens entirely new, previously impossible windows on reality. For those unfamiliar, quantum mechanics describes the bizarre, counterintuitive rules that govern how particles behave at the very smallest scales. Entanglement is one of its strangest phenomena. 2 particles can become so deeply correlated that measuring a property of one particle instantly influences the corresponding property of the other, regardless of the distance separating them. Einstein, famously uncomfortable with its implications, called it spooky action at a distance, but decades of experiments have confirmed that it is very real, and now engineers are racing to exploit it. The principle of a quantum telescope, as best as it can be understood from the limited available descriptions, involves generating pairs of entangled photons. One photon from each pair is sent out to interact with a distant target, while the other is kept within the detector. When the returning photon is measured, the information gleaned from its entangled twin allows for a reconstruction of the image with a precision that should be physically impossible. This could allow telescopes to detect incredibly faint signals buried deep within cosmic noise, to resolve fine details currently blurred by the laws of diffraction, or even to image objects using wavelengths for which our traditional detectors are completely blind. For astronomy, the implications are staggering. Exoplanets, currently just shifting dots of light, could be directly imaged with enough resolution to see continents and oceans. Distant galaxies could be studied in such unprecedented detail that we could watch individual stars being born. And closer to home, objects like 3 divided by Atlas could be characterized with a clarity that is currently the stuff of science fiction. Imagine pointing a quantum observatory at an interstellar visitor. Instead of merely inferring its composition from broad spectral lines, you might be able to detect the faint thermal emissions that could reveal its internal structure. Instead of just modeling its rotation from a simple light curve, you might be able to resolve actual surface features, craters, or facets, or perhaps even geometric patterns. This is not fantasy. The physics is established. The engineering challenges are immense, but they are not insurmountable. And if China, or any other nation, successfully develops and deploys operational quantum telescopes before others, they will possess an informational advantage that would fundamentally reshape global space awareness. The connection to the 3I divided by Atlas event is, at this stage, purely speculative, but it is deeply tantalizing. What if the ongoing observations of the comet have secretly included data from a prototype quantum sensor? What if some of the most baffling anomalies we've detected, the nickel emission, the extreme polarization, were only visible because these new quantum-enhanced instruments were involved in the campaign? That would elegantly explain some of the gaps in the public data. It would explain why certain findings seem to possess a higher degree of confidence than the disclosed conventional methods would seem to allow. It would also explain the intense secrecy, because revealing that quantum telescopes are now operational would be to reveal a strategic capability that defense agencies would move mountains to keep obscure. This is, admittedly, conjecture threads woven from hints and silences, but it fits the pattern. It helps to explain why the characterization of this object has been so rapid and so detailed, and why the official response feels far more informed than the publicly available data would seem to permit. A nation with an operational quantum telescope could monitor foreign satellites with terrifying precision, detect stealth spacecraft, and characterize objects in deep space with enough resolution to reveal not just what they are, but what they are made of, how they are structured, and possibly even what they are doing. That kind of capability is not just an advantage, it is a paradigm shift. Tianlong 1 might be mere propaganda, an ambitious claim designed to project technological superiority. But even if this specific system is overstated, the global trend is undeniable. The quantum revolution in astronomy is coming, and 3I divided by Atlas may have arrived at the exact moment of its birth, observed by the best instruments of the old paradigm, while the new paradigm stirs to life in classified labs and on secret test ranges. Part 12. The AI predicts the sky before it happens. Something fundamental changed in the field of astronomy last year, and most of the world didn't even notice. Machine learning models, trained on decades of archived telescope data, began to do something that still sounds like science fiction. They started predicting cosmic events before they happened, not through some mystical foresight, but through a process of pattern recognition so sophisticated it could see the future written in the faint signals of data we already possessed. In March of 2025, an AI system tasked with monitoring 3I, divided by Atlas, did something that made defense officials deeply uncomfortable. It predicted a major anomaly 72 hours before any human observer or conventional model saw it coming. The system, a collaborative project between JPL and the Minor Planet Center, had been ingesting every single data point on 3I divided by Atlas since its discovery. Machine learning thrives on patterns, and the AI had learned the complex, chaotic language of comets. On March 19th, the model flagged a high-priority alert. Confidence level, 87%. Predicted event, a significant, irregular brightening and a major outgassing pulse within the next 72 hours. The alert was routed to 3 groups simultaneously: the Scientific Discovery Team, NASA's Planetary Defense Coordination Office, and a Classified Defense Liaison Office. The scientists were intrigued. The defense officials were alarmed, because 72 hours is enough time to reposition strategic assets and prepare for contingencies. 68 hours later, almost exactly within the AI's predicted window, 3I divided by Atlas flared, brightening dramatically and releasing a massive burst of volatiles. The prediction was nearly perfect, and that's when the real questions began. Who gets access to this new form of predictive intelligence? If an AI flags a potential anomaly days before it occurs, do you announce it immediately, or do you wait for confirmation and risk being too late? What if the AI sees patterns that suggest an object is not behaving like any natural object in its vast training dataset? The March alert exposed a deep, underlying tension. Scientists demand transparency. Defense agencies demand control. An AI doesn't care about either. It just reports the patterns. This is the new frontier of planetary defense. Not just reacting to what we see, but acting on what a machine predicts we are about to see. and we have no rules for this. We are making them up as we go, and 3I divided by Atlas is our first terrifying live test case. Part 13. The Cosmic Energy Spike of 2025. On February 9th, 2025, instruments buried a mile deep in the Antarctic ice detected something that made physicists around the world check their calibrations. The IceCube Neutrino Observatory registered a massive burst of high-energy neutrinos, a cascade of dozens of these ghost particles arriving from the same point in the sky. The event was so powerful and so unusual, it was initially flagged as an instrument malfunction. Then, other detectors confirmed it. The event was real. Neutrino bursts like this are typically associated with the most violent events in the universe: a collapsing star, a gamma-ray burst. Scientists immediately tried to find the source, and that's when someone noticed the timing. The neutrino burst occurred just 18 days after 3I, divided by Atlas, had crossed into the inner solar system. Its trajectory had brought it close enough that its vast tail of gas and dust was interacting with our solar environment. Correlation is not causation. Every scientist repeats this mantra. The most likely explanation is that the neutrino burst came from a distant, unrelated astrophysical source, and the timing is a pure, random coincidence. But when you are already tracking an object with a dozen other anomalies, coincidence begins to feel like an insufficient explanation. Could an interstellar object, saturated with billions of years of cosmic radiation, release exotic particles or trigger energetic reactions as it interacts with our sun? We have always conceptualized planetary defense in terms of kinetic impacts, a rock hitting the Earth. But what if there are non-kinetic hazards? What if an object could pose a threat through radiation or energetic particle events without ever physically touching our planet? The neutrino burst probably has nothing to do with 3I divided by Atlas. Probably. But the fact that our defense agencies are now reportedly modeling these non-kinetic scenarios tells you everything you need to know about their current level of concern. Part 14. The Deep Space Firewall. There is a network that most people do not know exists. It has an unofficial nickname, whispered among those who work with it. The Deep Space Firewall. It is not a weapon, but an information architecture, a distributed system of satellites, ground stations, and classified sensor platforms designed to monitor everything beyond low Earth orbit. Its official mission is to track satellites and debris. Its real mission is to detect, classify, and respond to anomalies. 3I, divided by Atlas, triggered multiple flags in this system almost immediately. Its hyperbolic trajectory, its anomalous composition, its irregular light curve, each anomaly raised its classification level within the firewall. By late March 2025, it had accumulated enough flags to become a top-tier monitoring target for defense satellites that are normally used to watch for ballistic missile launches. This isn't public information. It has been pieced together from budget documents, leaked memos, and off-the-record conversations. The evidence is clear. A scientific object has become a defense operation. The problem is that the system doesn't distinguish well between unknown and dangerous. It defaults to treating anything unusual as potentially both. 3I divided by Atlas is the first interstellar visitor to arrive in the era of an operational deep space firewall. It is the first object to trigger these classified protocols. Whatever it is, it has shown us that the boundary between science and security has effectively dissolved. Observation is no longer neutral. Discovery now triggers a defense response. And somewhere, in secured databases, everything we are learning about 3I divided by Atlas is being analyzed through a framework that prioritizes protection over publication. The revolution happened quietly, but it has happened. Space is now a militarized domain. Part 15. The Threshold Moment. We began with a comet, and through its passage, we have discovered ourselves. We have seen our own technological capabilities, our institutional reflexes, and our deepest anxieties reflected back at us from the void. The profound disconnect between the official reassurance that all is well and the observable, unprecedented global response is the real story. We are witnessing humanity's first synchronized planetary defense posture, triggered not by a confirmed danger, but by the sheer, unnerving uncertainty of an object we can observe but cannot fully understand. This is a threshold moment. What if 3I divided by Atlas is, in the end, just a very weird comet? Then we have let our fears and our hopes project meaning onto something fundamentally random. We would not be the first civilization to see faces in the clouds. But what if it isn't? What if, after all the analysis is done, its signatures still cannot be reconciled with any natural model? Then we face an even harder question. How would we ever prove it? Any sufficiently advanced technology is indistinguishable from magic, or in this case, from a bizarre act of nature. We are trapped in the middle, lacking both a complete understanding of all natural possibilities and any framework for recognizing a technology we did not design. The precedent being set right now matters more than this single object. As our survey capabilities improve, we will detect more interstellar visitors. Each one will trigger this same cycle of discovery, anomaly, and defense coordination. The norms we are establishing in secret today will govern how we handle every future visitor. Perihelion is now just days away. The observations in the coming weeks will be crucial. We will soon know more about what 3I divided by Atlas is. Whether we will be told what is known is a different question entirely. And then, there is only the waiting for 4I, the next interstellar visitor, waiting for the day when an object arrives with properties so unambiguous that it forces us to choose between continued denial and a paradigm-shattering acceptance. That day may come next year or next century. But the infrastructure we are building today, in the shadows of this event, will determine how we respond when it arrives. The universe knocked on our door, we answered. We mobilized telescopes and satellites. We activated defense networks and classified protocols. We deployed artificial intelligence and our most brilliant human minds. We treated an interstellar comet like a potential threat because we have become a species that thinks in terms of defense before it seeks understanding. That says something profound about where we are as a civilization. 3I, divided by Atlas, is still out there, approaching the sun, indifferent to our anxieties. It is a messenger from the galaxy, perhaps carrying a message we are still too frightened to read. Stay alert, keep watching the sky, question the official narrative, but also have the courage to question your own assumptions. The storm may not be over. It may be just beginning, and we are standing at the threshold, caught between the solar system that raised us and the galaxy that surrounds us. What happens next depends on whether we choose to step forward with courage or recoil in fear. The sky is full of visitors. We are only just learning how to see.